Hello, this is Professor Keen. In my previous lecture, I discussed how it is not enough to simply appeal to the law of conservation of momentum in order to uniquely determine the outcome of a collision between two objects. In order to know the specific outcome of the collision, one needed to understand not merely momentum, but also one needed to know whether or not kinetic energy is conserved during the collision. In particular, if the kinetic energy is conserved during the collision, we call it an elastic collision. And in the event that the kinetic energy is not conserved, we call that an inelastic collision. In such a case, some of the kinetic energy of the objects colliding is transformed, for example, into heat or into sound, or perhaps there is kinetic energy added in terms of chemical energy, like during an explosion, let's say. In any case, I think it's interesting historically, in the 1600s and the late 1600s, early 1700s, when Newton was writing, there was a debate about what were the most significant quantities to consider when understanding the motion of objects. Newton tended to prioritize momentum, and that is why he comes up with this law of conservation of momentum. And Leibniz, who you might know also from as one of the developers of calculus, he prioritized kinetic energy. He thought that was the most significant quantity in understanding motion. And as we discussed in the previous lecture, actually, they were both right. It was important to understand both momentum and kinetic energy in order to understand collisions. In this lecture, what I want to do is present a graphical way of solving problems like this. I'm going to kind of sketch this out. I'll do this once, and I'm not going to go through all the details, but I want to present a graphical understanding or a graphical approach to collision processes or to collisions. Okay? So let's first consider, once again, the collision between two objects. We'll call this object 1 and object 2. And object 1 and object 2 are moving with some initial velocities v1 and v2. And I got that backwards. Let me actually do it the same example that I gave last time. So let's have object 2, object with mass 2, moving with the speed of 2 initially, and the object with a mass of 1 moving with the speed of 1 initially. And as I talked about before, we can discuss the kinetic energy before the collision. So the kinetic energy before the collision is given by the following formula: 1/2 the mass of object 1 times the velocity of object 1 squared plus 1/2 the mass of object 2 times the velocity of object 2 squared, and that is equal to the total kinetic energy before the collision. Okay, now what I'm going to do is I'm going to rearrange this formula a bit and represent it graphically. So what I'm going to do is I'm going to divide both sides by the kinetic energy. So divide everywhere through by the kinetic energy, and then rewrite this as v1 squared over, and I'm going to put the mass in the denominator. So 2 times the kinetic energy over mass 1 plus, you'll see why I'm doing this in a moment, v2 squared over 2 times the kinetic energy over mass 2 equals 1. Okay? And then what I'm going to do in a suggestive way is write this as v1 squared over a1 squared plus v2 squared over a2 squared equals 1, where a1 is going to be 2 times the kinetic energy over mass 1 square root, and a2 I've defined as 2 times the kinetic energy divided by mass 2 square root. Okay, so here is this formula that I've developed, which is simply an equation relating the speeds and the kinetic energy. And the reason I'm writing it like this is because you may realize that this is the equation of an ellipse. So if I make a drawing here of this formula, and if I were to put V1 on the horizontal axis and V2 on the vertical axis, this is the equation of an ellipse. Sketch the ellipse right here. Right? And A1 is the size of the major axis, and A2 is the size of the minor axis, or the semi-major axis and the semi-minor axis. Okay? So every point on this, that is every pair of points, so if you pick V1 and V2 such that you're looking at this point, those two objects with those velocities are going to satisfy this equation. That is, they're going to be equal to whatever that kinetic energy is. Okay? Now, let's consider momentum. So the momentum what's the equation for the total momentum? So this is the kinetic energy, now the momentum. So the total momentum of this system is equal to the mass of object 1 times its velocity plus the mass of object 2 times its velocity, right? And let's rearrange this formula a bit. So let's move this mass and velocity over to this side. So m1 v1, got a minus sign, the total momentum of the system, and that equals m2 v2. And then let's divide everywhere through by mass 2. And then what I'm going to do is I'm going to rearrange this equation. So these m2's cancel out, and so you're left with a v2. So let me just go over here. So this is going to be the same as v2 equals negative m1 over m2 times v1 plus p over m2. Now notice that this equation here, insofar as the masses are given and the initial momentum is given, this is the equation of a straight line. So v2 equals, this right here would be the slope of the straight line, and this would be the intercept. I guess we'd call it the v2 intercept. So this looks kind of like y equals mx plus b, right? Where this would be on the v2 would be on the y-axis, v1 would be the x-axis, this would be an intercept, and this would be the slope. Okay, and in our particular case, if we plugged in our numbers, we would find that this equation is the equation of a line that looks like this. So this is the conservation of momentum line, and this is the kinetic energy, I guess a kinetic energy ellipse. I guess I don't want to call that the conservation of momentum line. I guess I want to call it the momentum line. Because we're not really talking about conservation yet, but momentum line. And the intersection points here, right here and right here, I'll highlight them, this point right here and this point right here, are the values of v1 and v2 that, so this one right here is going to have a certain value of a pair of values v1 and v2, and this point right here it represents a pair of values v1 and v2 that are consistent with this system having a certain kinetic energy and a certain total momentum. So right here, this point represents, let me go back to this point right here. Let's start with this point right here. That is when the velocity of object 2 is plus 2, and the velocity of object 1 is negative 1. So that is this initial condition right here. So that is when, if you kind of project this down right here, velocity 1 is negative 1, and velocity 2 is 2. So that is this condition right here. The momentum holds, the total momentum has a certain value, and the total kinetic energy has a certain value, and that's that point. This point right here would be the outcome of the collision that has the exact same kinetic energy. So that outcome would be the case that I considered in my last lecture, where object 2, the velocity of object 2 is 0, and the velocity of object 1 is 3. So that would be the case where after the collision, I'll write it down here, where object 2 is sitting still and object 1 is moving to the right at a speed of 3. You might recall that in this case, the total momentum was the same in this case as in before the collision, and also the kinetic energy in this case was the same as before the collision. So they're both lying on the same kinetic energy ellipse, and they're both lying along this line right here. So this would be the situation, this solution of the intersection of this line with this ellipse. The solution gives you what the situation before the collision and after the collision are. So there you go. There's a graphical way of understanding these sorts of collision scenarios. It's a little bit mathematically more challenging, but I thought it'd be nice to illustrate that for you all.